Hi, my name's Gregory and I represent Hydrocarbon Program Consultancy. I'd like to welcome you to the Lubrication Reliability Virtual Summit 2022, and in particular my presentation on the PF interval failure analysis, basing on used oil analysis and statistical data. Now, some time ago I was asked by a manager from a company that I work for, how do you define the PF interval? Explain it to me in simple terms, Greg. Right, so I did research over the internet, as all of us do, on how are we going to apply the PF interval? How do we explain it? And looking at condition-based technologies, like where does it fit? My particular background in oil analysis, I believe that a chemical signature, you have the ability to make that change, before it becomes a permanent fault frequency. Others might disagree with that, and that's fine. We all have our strengths in our different CM-based technologies, right? So I looked at basing my assumptions on conveyor drive gearboxes and feeder drive gearboxes, and how we could go about tracking and trending those analytes, right, to reduce those failures or eliminate them and get them down to design life. So if we define oil analysis on the PF interval curve, it gives us a way of tracking and trending chemical signatures or analytes. Right, so by monitoring these signatures, set with stringent alarm limits, we can then look at eliminating functional failures, right, or reducing the amount of functional failures, be it whether it's an environmental condition, an operating condition, or a lubricant behaviour, to be able to get the most out of our design life. Right? So we have to have those predefined sets of limits so that we can create that. And we get that from statistical data. We can gather that statistical data, whether it's from maintenance management systems such as SAP, Maximo, Pronto, etc. We look at CMU readings, right, so that we can time how long we're getting out of an oil drain interval, etc. And then we can base those assumptions around our criteria for the asset integrity or the criticality rating of that asset to the business. Okay, so most OEMs, like, will give you around a 10,000 hour. We may have 2-year oil drain intervals, etc. Like as far as being able to honour warranty side of things. As the site matures, right, it can then start to develop its own lubrication and oil analysis program, and this is where the PF interval becomes very important for us, like, to be able to do that. So as I go through this presentation now, we're going to talk about 3 different conveyor drive gearboxes and a feeder drive gearbox, right? And in particular, if we look at case study number 1 and number 3, right, the gearboxes are identical, used in different applications, all right? And being able to base our determination on statistical data, right, to set those limits and get life extension, like, from that. So if we look at the conveyor gearbox study, right, case study, here we're looking at 2 conveyor drive gearboxes operating in different environments, utilised in different functionalities. Gearbox number 1, right, it's a crusher discharge conveyor. Right. Gearbox number 2 is a grinding mill recycle conveyor. Both fairly small dollar value conveyor gearboxes, right? But in different applications, the asset integrity, right, or the criticality rating for those gearboxes are quite significant. If we lost that recycle conveyor for the mill, right, then we lose our whole processing operation, right? So if we look at the data that showing on the screen here now, right, we've got 4 failures, 15 oil changes. We've got a gearbox value in Australian dollar terms of $8,820 and an average oil change of $700. Average gearbox replacement, right, in the maintenance management system, due to some of the different resources that are required, $12,500. If we look at the other side of it, right, on the case study number 2, we've got 2 failures there with 11 oil changes. Again, gearbox value and oil change values are the same, right? But the average gearbox replacement, 18,630, okay? So case study number 2, it had a criticality rating of 1, whereas case study number 1, it had a criticality rating of number 3, right? Because of that redundancy in that part of a circuit. So here we've got the statistical data on the crusher discharge conveyor drive gearbox. Now this gearbox was prone to work in a very dusty environment, and we were replacing this gearbox, like every year or every year and a half. Dirt ingress was incredible. We tried a number of different factors on repeated oil changes, etc. And I apologise for the size of the tables on the left-hand side of the slide, not being able to have the figures very clear. But if we look at green, we're looking at the oil changes. If we look at the reds, we're looking at the gearbox replacements. So we've got 4 gearbox replacements and we've got a number of different oil changes. Okay, the graph on the right-hand side, the upper graph, is giving us some very real indications as far as iron wear and then also dirt signatures. And if you can look at it quite clearly, we're looking at lockstep trending going on there. So dirt signature is creating ferrous wear. The image there is showing some very real damage to the input shaft, okay, the high-speed input shaft going to the bevel gear, driving the actual head drum of the conveyor gearbox. Okay, so we looked at it, and then by applying some simple filters, as far as eliminating the ferrous wear, I started to identify dirt signature as that trend. Okay, not a lubricant breakdown, not oxidization or anything like that, but dirt signature. So I reversed that and started looking at lowering those limits down, as far as dirt signatures. And the table at the bottom clearly defines as far as where we are, by eliminating all of the gearbox replacements. And if we eliminated the gearbox replacements, right, we then started eliminating oil changes. Right? And that was how we got to a stage of setting the alarm limits for dirt signatures. Now, some might say that they're unrealistic goals and measures, but you need to be able to set a benchmark on where you can sit to be able to maintain to get asset life. And the data was showing clearly that if we could maintain it with a ppm for silicon, right, of 3 ppm or lower, okay, we were reducing all of the additional maintenance tasks associated with that gearbox. All right, so we eliminated how 5 gearbox failures and the 13 oil changes had been removed. Right, some of the biggest impacts there were actually killing this gearbox with kindness by lubricating that input shaft seal, right, to prevent contaminant from getting in. We were starting to present with thermal expansion and contraction, and it was drawing the contamination in. All right, so further engineering changes to that gearbox in that application, right, eliminated all of these types of things going further forward. But again, statistical data, all right, what was the functional failure of that gearbox, all right, gear wear, and what was the leading indicator of that? Dirt ingress. So here again on case study number 2, we've got exactly the same gearbox, but in a different application, the grinding circuit, recycle conveyor, small gearbox as far as monetary terms, all right, but a large impact on process. And again, we had that dirt signature going on as the leading indicator, right, for damage and generating oil changes to the compartment. And because of that, we applied that same principle as far as the dirt signature alarm limits, lowering that ferrous wear generation. So again, if we come over here and we look at the graph or the table on the right hand side upper, right, by eliminating or lowering down the dirt signature, right, we reduce the amount of oil changes down to 2 in that history. Right. We had then been able to only look at a random event as far as dirt signature, right, generating an oil change parameter. Right. We go down the bottom, right, and we look at, okay, all of our failure modes, right, have disappeared. Right. So again, statistical data, right, the PF interval, right, being able to make those physical changes through oil analysis so that we can eliminate what the root cause of the gear wear is, right, and therefore reduce the amount of additional maintenance tasks associated with that asset. Okay, we can get back to a condition-based or even a precision-based maintenance regime. Here we continue on and we're looking at case studies number 3 and 4. So different gearbox drives, different applications, be it whether it's vibration, be it whether it's overloading, etc. So we've got 2 drives operating in different environments, right, utilized in different functionalities. Right. One's a mill feed conveyor, right, and the other one is a reclaim feeder gearbox. So high speed, moderate loading, whereas case study number 4, slow speed, high torque loading, subject to stop starts, and we've got some different dollar term values. So case study number 3, again, we had 2 failures, 9 oil changes, right, gearbox value itself, $36,412, oil change price, right, $1,077. So the total value of doing a gearbox oil change, a gearbox change, 52,000. If we look at case study number 4, a similar amount of failure modes and a similar amount of oil changes, different dollar values when you look at the 2 portions of the feeder drive gearbox, the planetary or the reduction. Oil changes, nice and easy access. But again, quite a substantial dollar value when it comes to doing the work on this gearbox. So with case study number 3, we went about it a little bit differently. Okay, so this is a mill feed conveyor, right? So moderate speed, high load, constant running, and again, we had that dirt ingress. Okay, we had that ferrous wear that was being caused by the dirt. Right? However, the dirt signatures weren't that excessive. Right? And what we wanted to do was understand what limits we needed to base to reduce the amount of oil changes and the amount of gearbox replacements. Right? So if we look at the table or the graph down the bottom, okay, we've got iron and we've got PQI, quite substantial, right? So we looked at then being able to lower, right, those limits down, right, and set an alarm limit, right? So by maintaining our dirt signature, again below 3 ppm, like our aluminium, our silicon and our sodium, below 3 ppm, we lost our ferrous wear, right? This in turn minimized, right, the failure mode. So therefore the failure mode in this instance was again the ferrous wear and the large iron wear, the PQI, right, from gear and shaft wear, and the leading indicator was the dirt signature. However, we based our alarm limits for this gearbox in the application purely around the PQI, and if we maintained a level less than 10 ppm, okay, our failure modes and our oil changes went away, right? So when it comes to setting alarm limits, it also means that we need to have a not one size fits all, but pick alarm limits specific to the asset and the application that it's being operated in. Right, so the above tables, they demonstrate that how the 2 failure modes and the 8 oil changes, right, have been removed, right, out of this application. Right, so again, the importance of statistical data, right, in oil analysis, being able to give us some real indication, right, in our PF interval on how we can get asset design life. So case study number 4, right, in this presentation is a feeder drive gearbox, and for those of you that are familiar with this type of arrangement, I think it was a Bravini Ritadori and planetary drive and a reduction gearbox. Okay, so high torque loading, low speed, dirty environment, right, that they're operating in, and again, we were having repeated oil changes, like because of dirt ingress causing ferrous wear material, and therefore 2 gearbox replacements and 6 oil changes, right? So what we needed to do was understand what was going on with our lubricants, right? So we had our dirt signatures, and again, we maintained a dirt signature below, but what we were finding in this was we were having a high oxidation level, so we looked at trialing different types of lubricants, like increasing in viscosity due to the oxidation or the thermal degradation failure. We looked at going with synthetics. We were finding that The dirt ingress, like on these assets was questionable, like whether it was from breathers, from maintenance inspection activities, whether it was soiling arrangements, and until we got to a stage where we were looking at maintaining and doing some engineering improvements, we had to get design life out of this. We had to get oil life extension, right? So we looked at some of the governing limits or alarm alerts, sorry, and we found the oxidation level. If we were maintaining an oxidation level, right, below where we were sitting at this moment in time, and here we're talking about keeping it below a 5, right, then we were finding ourselves in a better position, right, to get oil lubricant life, to be able to minimize our wear by oil degradation. So I mean, further down the track, we looked at some oil cooler improvements. We looked at better soiling arrangements, better types of breathers, better types of oil condition monitoring practices. But all of these worked hand in hand when we were trying to identify how we were getting these root causes down. We needed to maintain the levels below, right, from a 3 ppm for dirt signature, right, and an oxidization level, right, to be able to then eliminate the gearbox failures. Like these gearboxes are designed to go for 10 plus years. So we were finding over the course of 4 years, 5 years in this case study, right, we had changed these guys out twice. Right? So again, statistical data, the PF interval, where are we at, how are we going to continue monitoring, and then reverse engineering so that we can steer away and get us back to a scheduled maintenance interval and reduce our maintenance costs. So once we've reviewed all the data, it then allowed us to generate a set of limits based on the application for the component, the lubricant being operated in the equipment, or the operating environment. And depending on rotational speed or load or contaminant exposure level, using that data from the PF interval, limits were generated against these components. These limits can't be applied to everything. They have to be specific to the asset and the environment and the lubricant used, right? But a good general guideline, as far as your oil analysis program, right? So control and alert limits, they can be generated using a number of methods like statistical analysis, right? Or a technique offers another way by reviewing the CMMS, right, the SAP data, right, and oil analysis to set these limits. If we continue on, right, and use standard deviation, we can then go one step further against each of those assets. So if an asset has a high speed and a moderate torque loading, right, the PQI and the FE will be greatly affected by the level of dirt exposure, right? Silicon, aluminium and sodium. Here we've got a little bit of iron being one of those causes, right? If an asset had a low speed with a high torque loading, right, PQI and FE are greatly affected by the oxidation level, right, in this application. So in summary, after looking at the 4 case studies and generating those control limits, right, an asset of rotating design has a defined design life. If the asset is maintained within permissible limits of contamination, there would be an expectation of meeting that design life. By applying PF interval model, filtering the data revealed that a minimum limit of contamination removed the majority of all maintenance activities and failures. Limits are dependent on rotational speed, load, and contamination exposure level. If an asset has a moderate speed and a moderate torque loading, PQI and FE will be greatly affected by the level of dirt exposure. If an asset has a low speed, high torque loading, again the ion generation, greatly affected by oxidization. By establishing and maintaining limits based on the analysis of data, clear documented evidence supports the encouragement of contamination control. And we use this as part of our contamination control program, right? And also our oil analysis program on how to reach that design life. So in wrapping this up, I'd just like to thank you, for listening to my segment on the PF interval using statistical data, right, to highlight lubrication related failures within asset and the asset integrity. My time slot is on Thursday, and depending on your location within the world, different time zones apply. If we look at how you can get in touch with myself, we're available on all types of platforms. Cross between tablets, mobile phone, desktop computers. A little bit about us, Hydrocarbon Program Consultancy. Okay, we operate within Australia and PNG. We have other destinations as client interest grows, but majority within the South Pacific region. We work in very closely with a number of large-scale clients like Newcrest Mining, Octetti Mining Limited. We work with a power station generation company, other labour companies applying lubrication technicians within their workforce. Our company itself, or myself, we're based in Orange, New South Wales in Australia. My contact details are there, and I'm quite easily reached on the Australian mobile number or the PNG mobile number if you can't get me on the Australian. Email address is there, or a contact form on our website. And I thank you. I've put in there that the moderator can forward any questions to my email address, and I hope you enjoy the rest of the Lubrication and Reliability Virtual Summit 2022. I thank Sonia and the team for approaching me to present at this conference, and I wish you all well in the future. Thank you very much.
Are you able to hear me now? No? Okay. Okay, well, finally, I'm so sorry for that. Well, anyway, thank you for your time. And then I will end up quite quick as time's finished. Well, as the speaker already listed his email address, so if you have any questions, you can contact him directly with his email address, or you can also leave your question on our platform, and then we will link your question to the speaker as well. So thank you for your time once again, and bye.